Now we have looked at the weak forms, and all the weak forms are of the type uh, del W internal is equal to del W external. The del W internal can be composed out of say sigma and d, in which case it's a principle of virtual power. It can be composed of P and delta F, it's a principle of virtual work, then S and delta E, principle of virtual work again. But whatever be the conjugate measures of stress and strain used to describe your virtual work or virtual power expression, it always has this form. So if we write del W equal to del W internal minus del W external, then this is equal to 0. And now for, let's say, a principle of virtual power, which is in the current configuration, we had written that internal virtual work is this, equal to the external virtual work plus, so this is the external virtual work due to body force, due to surface tractions. So once we write it like this is your internal virtual work. The right hand side is the external virtual work. So when we write it like this, then del W is a function of the displacements and an arbitrary variation in the velocity del V. So this has to be equal to 0. This has to be equal to 0. Now we will make a distinction between two kinds of subscripts and superscripts. In a nonlinear problem, we sometimes increase the loads, so we do not apply the B or the T all at once. We sometimes do it in bits, bit by bit. So we have a time step which marches on. So if you have to reach a B of 100, you can do it in 100 steps and in 100 time steps. The time is a pseudo time. The time does not actually have a meaning, but it's something like a counter that keeps track of how much load you have applied. So let us say I have obtained the solution UK at time tk, and I now want to obtain the solution UK plus 1 at time tk plus 1. And to do that, I will use the Newton-Raphson method on this fact that del W UK plus 1 comma dV, it's a function of delta V, because I am using this weak form in the current configuration, and this quantity has to be equal to 0. I will do Newton-Raphson to find a suitable UK plus 1 that satisfies this equation for an arbitrary delta V. To do that, Newton-Raphson, we again do the linearization of this. So UK del W at the I plus 1th iteration is del W at the ith iteration plus the directional derivative of del W in the direction of delta Ui, where delta Ui is the correction to the value at the ith iteration of UK plus 1. So here there are two subscripts, a subscript and a superscript. So the subscript is the time step, is the k plus 1th time step, and within that time step the superscript gives you the iteration number. So this is the I plus 1th iteration to the displacement function, displacement vector UK plus 1. And to get this, I need this quantity, and this quantity can be obtained by solving this equation like we had done in the previous lecture. And if you can solve this equation, you can find delta Ui, which you add to the value at the ith iteration to get the I plus 1th iteration. Again, you keep doing this till these two things become equal to each other by some measure. So this is the equation that we need to solve in nonlinear finite elements. And very often, since you know the solution at UK, the 0th iteration, the first guess to solving UK plus 1, is most often the value at the kth time step. That's used as the first guess for this iteration loop. So let us stay with what is known as the updated Lagrangian formulation for a while. Updated Lagrangian formulation implies that we are starting with this principle of virtual power as our starting weak form for the finite element formulation. Now we are looking at an isoparametric formulation. Looking at that, we will make this discretization. So for an element, let's say a four-noded quadrilateral E. You have four nodes. The nodes are denoted by capital I. The directions are denoted by I. So for this case, small I will go from 1 to 2. Capital I will go from 1 to 4. So you can write xi at any point inside the element as the shape function which interpolates times the values at the nodes. Remember, these are values at the nodes. This together, this has always got to appear together, the small and capital, and this will go to a Voigt index of A, which is given as into the dimension of the system plus I. So I capital I will map to Voigt dimension A, which is calculated like this. We have done this before, so I'll not explain it any further. So now you have xi. You can go ahead and formulate the other quantities. So ui, the displacement is xi minus capital Xi being the initial coordinate, and um, and you can, in isoparametric formulation, we use the same shape functions to interpolate ni, interpolate ui. So we use the same shape functions capital Ni to interpolate, and these are the displacements at the nodes of the element. Vi is the same. The velocities at the nodes are done in the same way. So the same shape functions are used to interpolate the nodal values of the velocity. Derivative of this, remember, we need to calculate delta ij, which is half delta vi del small xj plus delta vj small xi. So these are derivatives with respect to the current configuration because you are using an updated Lagrangian procedure. So we need to get, say, vi comma j, which is easily obtained from this. So vi comma j would be n capital I comma j. These are not functions of position, so they will remain as such. And here you have to remember that these are derivatives with respect to the spatial coordinates, and therefore dij would be half of vi comma j plus vj comma I, which is half of n I comma j vii plus n I comma I vji. So this is what dij would look like, and delta vi would be the same. So if you do delta vi, it would be the same, and delta di would be simply this. So you have to replace these by deltas. So now I take this delta dij and I plug it into here. So this is sigma ij delta dij dv, and I plug it in here, and if I do that, this is what will result. This is what will result actually over the element. Now we are doing everything over the element. Delta vi is an arbitrary function, comes out of the integral, and you're left with this. Now this whole thing, we can further define a quantity del ni del xj. So the spatial derivatives of n, we can define a new quantity bji. So we can replace this one, we can replace it by over the integral bji sigma ij dv times del vii. So this is j is a repeated index. So this is ii. The order doesn't matter. Times vii. So this is a dot product between delta v and this quantity, and this quantity we can call it the iith component of the internal force. So this uh, virtual velocity times this internal force, the nodal equivalent internal force, gives you the internal virtual work. We do the same thing to the external virtual work. So in place of um, so the external virtual work, remember, was b dot delta v, and here I can write it as bi delta vi. In place of delta vi, I put n capital I delta v I times dv. Delta vii comes out, and I'm left with bi capital Ni dv. So this is the external force, nodal equivalent external force for the body forces. Similarly, this is for the surface tractions, and then this times so let me add the surface traction also. So this times this whole thing, which we call F external, FII external, is the work done, virtual power due to the external force. This we have derived for an element. We have to assemble it to get F external for the whole system, F internal for the whole system. That assembly procedure, I guess you already know. Assembly of vectors is pretty straightforward, and then this is what we have to solve. F external can be a function of the displacements u. F internal, of course, is a function of displacements u, and then we have to find an u that satisfies this expression, and we will do that by taking F internal of u minus F external of u, this system of equations, equal to 0. We'll use Newton-Raphson in order to find a u that satisfies this expression. So that is the crux of the problem, and we have done this in case of an updated Lagrangian technique. We can also do it for the situation where we have a total Lagrangian. We want to apply a total Lagrangian. For total Lagrangian formulations, we start with something like this. In the reference configuration, a virtual work equation maybe. We can also start with something like this, a virtual power equation in the reference configuration. Let us show the procedure for this case. You can do this case on your own. Let us show it for this case, which is very similar to what we have done in the previous example. Again, xi, the position vectors, are ni times xii, and displacement components are interpolated in exactly the same way. Delta ui is this. So now I'll have to do del fij times del fij pij. So del fij we know is delta del xi by del capital Xj. This is del Fij. We have derived this before, and now go from here. You will get del capital Ni del capital Xj times Xii. So this now are derivatives of the shape function with respect to the reference configuration. These are material derivatives of the shape functions, and you have to be careful about that. This can, of course, also be written in terms of ui, but this is what we will stick to, and this we will now define as a new vector bji0, just like we had defined this ji. Now we will add the 0 to indicate that the derivatives are with respect to capital X and not small x. If you plug it in now, if you plug this in, then again delta UII comes out. So Fij can also be del Fij can also be written as del Ui del capital Xj, because remember that Fij is delta ij plus del ui del capital Xj. So this was also something that we had derived from there. You can write this as well. So this can be written just like this, can be written as del n capital I del capital Xj times delta UII. So this is how you can also write it, and this will be Bji0 delta UII. This is not a function of position, comes out of the integral. You are left with this quantity. This is your F internal II. So this together is the work done, internal work, virtual work done by the internal forces. Similarly, you have the work done by the external forces. Remember that now we are using the pulled back, or BI0 and TI0, the traction and body force components that are appropriate for the stress measure that we have used. So in this case, the stress measure that we are using is P. So this B0 and T0 have to be commensurate with the stress measure that we are using. We have discussed this point before, and this is again this becomes FII external. This becomes FII external. So again, you are left with an expression F internal equal to F external, which you then have to assemble, form it for the whole system, and solve that through Newton-Raphson in order to find the U that satisfies F external equal to F internal. Though the final expression looks the same, the path to the derivation of F internal is not the same, because in the previous case, in the updated Lagrangian technique, it involves taking derivatives, spatial derivatives of the shape function. In this case, it involves taking material derivatives of the shape function. There's a bit about the maps, different maps involved, that I wanted to talk about. So you have the parent element, which lives in a coordinate system which we have denoted by zeta, and then you have the physical element in the reference configuration, which we will denote by this, and then you have the physical element in the deformed configuration, which we denote by this. Now there's a map. Any point here can be mapped onto equivalent point here by this map capital X of zeta t. This point can be mapped onto a point on the deformed configuration by this map small x of zeta t. And of course, we have a map from here to here, which we denote by small x of capital X t. So these are the various maps involved. And remember, when we are doing the total Lagrangian or updated Lagrangian formulation, we have to take derivatives of Ni with respect to, say, capital Xi, or derivatives of Ni with respect to small xi. So spatial or material derivatives. And to do this, we will have to use either this map or this map. And this is how we will do the spatial derivative. Suppose I have to do Vi. So Vi is at any point is Ni times Vi. We have seen this before. And if you want to do del Vi del small xj, you will do del capital Ni del small xj VII. Now this is a function of zeta. N is a function of zeta actually. So this would be let's say zeta k del zeta k del x j VII, and this quantity is the inverse of the Jacobian. We call this Jacobian J zeta in order to distinguish it from determinant of f, which we call J. So this is the inverse of the Jacobian and the kjth component of that. So that is what comes in here, and this has to be calculated taking the derivatives of zeta with respect to the spatial coordinates. So this is our basic assumption for the discretization of space. So xi is xii ni. Ni is a function of zeta, and all the time variation is here. So at time t equal to 0, these quantities are just capital Xii. So at time t equal to 0, this interpolation specializes to capital Xi. So this small xi becomes capital Xi at t equal to 0, and then these become the nodal coordinates at time t equal to 0. So this is how we handle the various mappings. And if you have to take derivatives with respect to capital X, then you have to know the Jacobians, Jacobian and its inverse, and the Jacobian would then involve x, capital Xi. This would be g zeta 0 ij, and that will allow you to take derivatives with respect to capital X. When when you find out, say, FII, and you use this to find out FII, you obviously don't integrate directly over the physical space, you integrate over the parent space, and then change this to j zeta times d. This is, in our case, d zeta 1, d zeta 2, d zeta 3 for the 3D case. So this is how we do integrations. This is similar to what we use for normal finite element, linear finite element. Only thing that you should keep in mind is how to calculate this quantity. And to calculate this quantity, you have to use this transformation, in case where you need spatial derivatives of n, and transformation using this in case you need the material derivatives of